Yeah, I guess we'll get started. Thanks, Andre, for being here. So Dr. Andre Perkins received his PhD in atmospheric science from the University of Washington, where he studied new ways to reconstruct the last 1,000 years of climate using a combination of data simulation, climate models, and proxy records. Currently, he's a senior research scientist at the Allen Institute for AI in Seattle, Washington. He works to improve weather and climate predictions using ML, which is very much in sync with what we do here at LEAP. That's why we invited him. And his current research interests include ML-based emulators, which he's going to talk about more today, diffusion-based downscaling, in addition to compute performance optimization, as well as cloud computing management. So without further ado, please take it away. Thank you for being here.
All right, great. Yeah, as he said, I'm Andre Perkins, research engineer at AI2, a little bit maybe more nebulous of a title, but basically do a lot of coding and a lot of research on the team. And most of the team is kind of some mix of that. But yeah, excited to talk to you today about how we're trying to use ML to improve climate modeling. Yeah, and at any point, I think because I can hear the room, you can maybe speak up because I might have a hard time seeing hands. So feel free to interject at any point with questions, and I'll try to also look at the chat. So a bit about AI2. We're really concerned with building breakthrough AI to solve the world's biggest problems. And specifically, we're a special kind of place because it's a nonprofit research institute. So it's funded primarily by the Paul G. Allen Family Foundation, but we do have some extra support from federal agencies. But we're really focused on core AI topics and applications. This obviously is maybe more thought of as traditionally natural language processing, computer vision, and robotics, but we also have a very strong commitment to open source and open data. So, the advances that we make can benefit the public and benefit people more broadly. So if you want to see an example of some of the latest work, Olmo is the fully end-to-end open source LLM that the company is developing. But I'm on climate modeling, and that's not really in any of those sub areas. So we actually sit within a more applied team, AI for the environment, which encompasses some teams that are working on conservation, environmental monitoring, our climate modeling, and our climate modeling team. So it's a pretty cool mix of people. So I always like to start with just a really kind of basic full view primer of the climate modeling in general. I assume most of you maybe are familiar with this, but really what we're trying to do here is we have this real system with a huge, huge amount of different scales and very intricate processes and interactions that are all happening in real time on the planet. And for a lot of reasons, we're interested in how can we take that system and put it in a form compatible with computational prediction. Obviously start that by we need to, we can't represent it in infinite quality. So we discretize the planet to some grid that involves some determination of, how far apart do you want different grid spacings to be. And with that comes the trade-off of how fast does it run, how many assumptions you have to make about the physical processes going on beneath the scale of which you're actually resolving. But this is the general strategy that we use for modeling the planet. And we do that because we are very interested in exploring how things work. So to do that and run very controlled experiments, our only strategy for a lot of the biggest questions is to build these models. But of course, we're also interested in projections, predictions of what's going to happen next, what's going to happen in the next 10 days for weather forecasting, what's going to happen with the climate as we continue to release greenhouse gases. So while at this point we have decades of research and we're extremely certain that increasing CO2 is leading to increasing temperatures in many places, there's much less agreement about precipitation trends. So as an example, I'm showing a plot on the left of some ensemble members from the IPCC models. Mean temperature of Western North America is on the top half, while precipitation percent change is down beneath. And you can see, at least for Western North America, there's not really any consensus about, what's going to happen in the future. And that's very important for real impacts on people as they try and make decisions about water resources and management. And so it's very important information going forward. And there's not a lot of certainty about which way exactly that will go. So this is kind of how our group was born. We originally started at Vulkan, but then a different company under the Paul Allen estate, but then moved to AI2. And we started with our goal to reduce uncertainty about the 21st century local precipitation trends and extremes. And to do that, we were going to try and make climate models better. So some mix of machine learning using coarse grid climate models, and then also borrowing information from much finer resolution simulations, which we can't use on climate timescales. So with that, we closely partner with NOAA GFDL because they are developers of a very high resolution weather model, but we also have ongoing collaborations with other R&D groups, notably Lawrence Livermore National Lab and their E3SM model, and NVIDIA for their ML expertise. And then you can see a picture of some of our team members and collaborators below. So how can machine learning help with weather and climate models? Well, the primary strategies that are at play in this is that we can hopefully make them more accurate, but also make them much faster to run because you can run on GPUs using much coarser time stepping, much fewer degrees of freedom, and that hopefully will make it more affordable and accessible. So on the right, I have kind of our schematic of how you can incorporate ML with these models with sort of growing influence or control as the circles get bigger about what the ML is actually doing. So our team actually started out with using a lot of hybrid strategies where we're either replacing or correcting components of the model. So in that case, you're actually using the original atmospheric model that's still there. You still have the constraints of that model, but you're trying to strategically plug in ML to that to make improvements. For various reasons, we have really pivoted away from hybrid ML, and I'd be happy to discuss some of those reasons if people are interested. But most of our current work, which some of you may have seen at the M2 Lines annual meeting, has been on what we're calling full model emulation, where we're essentially using machine learning to learn the entirety of the atmospheric model or the atmospheric component of the model instead of running the traditional physics-based model alongside that. So all of the sort of results I'll be showing today are from the full model emulation side of the project, notably what we're calling ACE, or the AI2 Climate Emulator. So I'm going to highlight a lot of results here because I'm going to try and touch on, some of the projects that we are finished with, nearly finished with, and upcoming. So please, again, feel free to stop me at any point if you have some questions or want to talk more in depth about something I'm showing. So I'm sure folks are well aware that ML-based weather forecasts have kind of exploded within the last few years. A lot of the pioneering work, happened early in 2019 to 2022. Folks weren't really sure whether or not we could ever get to the point where these forecasts would be, better or more worthwhile than what we're doing at traditional weather prediction centers. But from 22 to 23, we saw an explosion of multiple models that were able to make improvements on 3 to 10 day deterministic weather prediction metrics. Now, the metrics they're selecting maybe don't cover all of the use cases, but even the fact that these fully AI-based models can make predictions of, really complex fluid dynamics and physics on the planet was quite remarkable. And with that, we're kind of moving, out of the nascent stage and into the application stage where there's an explosion of development, more so on probabilistic models that, make use of the fact that these models run very quickly and you can run a lot of them, but also more interesting developments in data assimilation and coupled atmosphere-ocean models. So we're sort of creeping towards, longer and longer time scales, which is also what we are interested in. So, well, most of the weather models, have great forecasting for sort of their training targets, which is short to medium term weather forecasting. They're trained mostly on 3 or 6 hour time step information about just predicting the next time step. So when you run these models out for longer times, they start to break down and they're not really useful or accurate or maybe even stable beyond 2 weeks. So this is an example plot of someone who took a lot of the latest weather forecasting AI-based models and simply ran them for long periods of time to see what they're doing. This is showing the zonal mean 500 millibar height over time at different latitudes. So you can sort of see the seasonal cycle as the atmosphere ebbs and flows with that. But you see for certain models, they just explode to all red, while some just degrade to a flat profile where there's no changes over the course of the season, which isn't interesting. So how do we build a model that is stable, retains that the characteristic weather forecast, but it is also useful for climate is sort of what we were interesting. So at the very beginning of this, to start this problem, we were going to train on climate model output. So instead of ACEv2 data, which most of the weather forecast models have been using, we're going to train on model output because we also can then train from a diverse range of climates. But with that, we also wanted to start simple. So instead of, going directly to realistic scenarios, we started on repeating climatological SSTs. So it's fixed external forcing, and used a relatively coarse resolution for our grid boxes, or how we're discretizing the planet, of 100 kilometers. And then we do provide basic boundary conditions, so forcing to the ML in this case, which is not happening in the weather models, but we're really focusing on how do we do long-term stability. So that was the very start of the ACE project. For our training setup, we're using the NVIDIA spherical Fourier neural operator as the backbone for our prediction. So this was released by NVIDIA. But we are still using a very similar loss function as in the weather case, where we're inputting at time t some basic state variables for the atmosphere, so humidity, temperature, wind, and some other fields, and we're just predicting, or we're conditioning the loss on predicting 6 hours ahead. So we're not going for any long-term climate metric loss scaling. We're just trying to do this, but we're adjusting slightly how the problem works. So we have forcing and prognostic variables in, and then we have the prognostic variables output, along with some diagnostic variables, which will help us constrain the state, as I'll talk about a bit later. And again, for the training data, we're using model output, so maybe a little, less realistic than, say, the ACEv2 data, but again, we can run at multiple climates. And for the purpose of machine learning, we actually coarsen the vertical levels to 8 terrain following finite volume layers on the grid we're using. So that's a bit for computational speed and reduced storage requirements of the data itself. But what we do in this coarsening process is we actually conserve the mass and moisture in the vertical coarsening. So we can calculate exact budget still, which is more important because we want this model also to be we want the ability to analyze this in more traditional ways that, say, climate modelers would look at this. So for the training data, we started with the original ACE. Again, that's the annually repeating SST forcing. So just the same year over and over, where each one is essentially an independent sample of the same forcing. We had 100 years of that data, and we withheld another 10 for validation. And then in some of our latest work, which I'll talk about later in the presentation, we have moved to historical SSTs, and then also a model which we'll couple to a slab ocean that we ran in a few different CO2 forcing scenarios. So again, working in this model space really opens up the door to do a lot of different types of training. And so that's been a very beneficial portion of our collaboration agreements. The variable set that we're using, again, just to reiterate again, we have some prognostic fields that go into the emulator along with some forcing variables. So for example, we're using solar insolation, sea surface temperature, the surface type fraction, say land, sea ice, ocean, and elevation. And then we also have quite a few diagnostics that we're focusing on, including precipitation, the top of atmosphere and surface radiative fluxes to check how energy is moving around, and some of the surface heat and moisture fluxes. Okay, so unless there are any, I guess, more specific questions about maybe the architecture or training data itself, I'll just start in on some of our ACEv1 results, and then I'll move into some of our close to publication and ongoing work. Okay. So results, what does the emulator look like in at least the first climatological SST forcing case? So after we trained this, we really didn't know what to expect, but even from the initial trainings, it seemed to be that it was remarkably stable and did a good job capturing the seasonal cycle. So this top plot is the lowest level in our emulator, so the boundary layer average temperature, along with the integrated water path across all vertical levels across a 10-year simulation for this. So the main point you want to take away from this is that the ups and downs of the reference, which is the blue line, and our emulator orange are very close. They track each other, and there's no large excursions. So stable model, which was the original goal, works a long time and maintains that some of the climatological variability of the target data that we're training on. But also, even with these long rollouts, it does maintain realistic aspects of weather variability. So right now I'm showing snapshots of OLR that are from, I think a year or two into the simulation, or no, for the first 100 days of simulation, so longer rollouts. But notably, we aren't explicitly resolving clouds or anything in this, but still the model is able to internally represent that and output fields of outgoing long radiation that look very realistic. You can tell it's a bit more smoothed out, but it still has that characteristic variability. The system looks like it's evolving as it should, which is a good eyeball norm test to start. And then when we do long-term runs and actually check out the climate, it also has really excellent accuracy at emulating the climate of the target data. So because we have 100 years of training data, we can essentially calculate a noise floor error of just from natural variability of the bias map that is shown on the left. So that's the 100 years of climatological SST data compared to the 10 years we held out. And then, so we do the same climatology for the ACE model and check against that, and that's in the middle, so it still retains very low RMSE pattern errors and very low bias. So mainly there's no large, blotches of red or blue there. And then we can compare it to more traditional resolution climate model in the baseline where we use a 2x coarser grid, run that model to calculate statistics, and it's notably better than the quote unquote climate model climate accuracy in this case. So a very good representation of the climate scale in this first attempt. And when we look at a larger set of the variables, the emulator itself overperforms 90% of the output variables that we're tracking compared to the coarsened climate model. So what about physical consistency? So with this model, we have humidity as one of the prognostic variables, so we can check the moisture tendencies in time to see whether the total tendency of moisture in the field would add up to what our known budget quantities is. So it's a combination of evaporation from the surface, precipitation, the water falling out of the column, and then advection moving water in or out of each individual grid cell. So when you subtract the total tendency from these three components, you would expect zero. The top row is the reference model for a snapshot, and the bottom row is the emulator 1 year into the simulation. They all should be zero, and they're very close. So even though we didn't explicitly train this initial model to have any conservation in it, it is very close to conservation, which was very interesting to see and not necessarily expected. So it's performing well there. But, close is not perfect, and we did look into some of the aspects of mass. So for our original emulator, which is the orange line here. We're just looking at global mean surface pressure over time, and you can see compared to the reference model, it kind of goes up and then goes all around from time to time. So there's the model doesn't necessarily know or think about, the fact that the dry air, the total mass of the atmosphere should be fairly set in the seasonal cycle. So because of that, we did actually, and we can calculate a budget from the way we formulated the actual data for this model. We do add dry air moisture and moisture mass corrections that T+1 is equal to the mass at T in training and inference. And once we do that, which is the green line down below, it gives a much better representation of the mass conservation and the expected seasonal cycle and the global mean surface pressure. So just some really simple tweaks to make this model sort of look more realistic and act more realistic that have worked to good effect. And then long-term stability. So climate models should be able to run for long periods of time. Here's just another example of the top was our original ACE model that we published, so no physical constraints. You do see the total water path has some maybe unrealistic gyrations over time where the annual cycle is too muted or too large. But once we do add our mass conservation corrections in here, it's stable for 100 years and maintains that cycle. So very easy to run, large ensembles of very long integrations here and have them work, which was great. So why do we think ACE is stable? Well, one part is that with the SFNO architecture was a much better than the original just 2D FFT based forecast net, which some of the weather model, the NVIDIA weather model started with. So this architecture itself seemed to be just very good at being stable indefinitely. But also we adjusted some of the normalization strategies so that we're using residuals instead of the full field from time to time. So we're actually just predicting a delta. And this helps us account for different timescales of different variables. And then, of course, adding in components of the forcing and diurnal cycles. So insolation is key for the seasonal cycle. But it actually turned out it was important to include some static fields such as topography to really improve this. But we haven't necessarily done rigorous testing exactly to show, what leads to stability and what not. But we do have a feeling that the finite volume terrain following vertical coordinate has some aspect to do along with the conservation constraints has something to do with this. And we were originally thinking, maybe it's because we're emulating model output and reanalysis, but you'll see later that also emulating reanalysis with this strategy works. So just to show that this is generalizable, one of our interns from a couple years ago who now works with us as a postdoc tried this exact same strategy, but on the Lawrence Livermore E3SM model, so EAMV2. Did the exact same project, but with that model and found very similar results. So this, the plot below is just showing that the ACE emulation of the model versus the original model compared to the left where we compared the original model against observations, the ACE emulation biases are much small and errors are much smaller than as compared to observations. And that's just to say it does a good job of representing the target climate. And we also got a chance to look at the precipitation, since that is, one of the focuses of our group from the emulator in this case. And the daily precipitation PDF also shows great agreement where we're pretty well capturing the general distribution, but also the far tails of precipitation, which is important for any model that you want to look at extreme. So very, very cool to see that. And then finally, for at least for the this initial work we were doing on ACE, one great thing about the SFNO model itself compared to some of the other state-of-the-art prediction weather prediction models is it's very cheap to train. So it was about 60 hours on 4 A100s, which is the previous generation's top of the line GPU. So within a few days, you have a new model to test and look at, which is very good for prototyping and experimentation, and relatively cheap to run. You don't need lots of GPUs to get at these quantities, which is nice. And then at runtime, of course, because they're simulated on a few GPUs and we're taking 6-hour steps instead of a few second steps, it's much cheaper to get really long simulations. So compared to the original FE3 GFS model, which we use for some of our simulation, we can get 1,000 simulated years per compute day compared to 15 at this resolution in FE3 GFS with a much lower electricity. But of course, the caveat here is with ACE, we're just writing out a subset, or we're maybe not writing out any data, whereas that is a big part of the plumbing in any computational model. So not exactly an apples to apples comparison, but just to show that it's good for running things quickly. Okay, this may be, if there are any initial questions about the first part, I can answer those now. Otherwise, we're going to go into, I guess, maybe some new stuff that folks haven't seen yet, which is our most recent work on historical SSTs and coupled modeling.
I have a question.
Yeah.
You hear it? Okay, cool. So you said that there was like realistic weather variability for the first 100 days of the simulation.
Yeah.
Just curious what started to become unrealistic after the first 100 days.
As far as I'm aware, it maintains that variability over time. So this was just a byproduct of the initial looks we were checking in the model. So it does retain sort of the I guess the spectral quality. If you just take a snapshot at any given time, it maintains that. There are some variables that do drift, notably the stratosphere. So the topmost atmosphere level is probably where we have some of the most issues. And that's primarily because the stratosphere has a much longer time scale. So even with the amount of simulation we have, it doesn't really well constrain the total space of variability in the stratosphere. And because of that, it's easy to overfit on that. So we've had to do some adjustments in the loss to try and make sure we weren't over focusing on the stratosphere, particularly because we don't know if we have enough data for that part of the atmosphere.
Yeah, thank you.
Could you improve that by changing the input data compression that you did from the 60 layers to the 8? Could you do that like less, do that less to improve the stratospheric modeling?
Yeah, so you're asking if we could adjust the vertical coarsening strategy to maybe give better information on the stratosphere?
Yeah.
Yeah, we have looked at different coarsening strategies to see how sensitive this is to that, and we haven't found a large impact yet of that. So that's part of the reason why we think it's more of a data issue than a vertical or a grid issue right now. But that's a good point. Okay. Let's see what time. 9:30. So the seminar goes until 9:50. So I got 20 minutes, I think. Cool. All right. So yeah, of course, climatological SST is a good first start, but not really that interesting from a climate modeling perspective. So immediately after this, we were curious about actual more realistic historical sea surface temperature and atmospheric trajectories. We trained a model on climatological SST. Could we just feed it historical SSTs and see what happens? So that's essentially a zero-shot prediction, or you're testing the model on data that it would have never seen before, or has qualities it has never seen before. The orange lines are FE3 GFS simulation forced with historical SSTs. So it's some training data that we will use to train a model. And then the red line is the original emulator we trained only on climatological SSTs. So you can see here, the red line is flat over time, so it does not react to rising surface temperatures at all. So the model really hasn't learned any effects of forcing or anything like that. But once we do train on data that has seen some amount of historical forcing, and test it on this period that is left out, we do actually see some trend line. So it is just a byproduct of making sure that your neural network has seen something that's in the space of familiarity. So we did, train on the whole historical period, leaving out the period where these yellow lines appear. So 2000 to 2010, so 10 years of validation data. Did the same process and then tested it for stability and also to see how it reacts to historical forcing. So the black lines are the reference. Blue lines are two different initial conditioned runs of 82 years, and this is the annual average lowest layer air temperature, so equivalent to surface temperature over time. You can see it does capture the trend quite well, but maybe for models initialized in the validation period, some sense that the actual internal variability is maybe a bit higher than would be expected. But again, the climatologies for these emulators trained on historical data is very good. So we have two different cases here. The blue line is trained on era 5 data. So we have the reference is the dashed line, the blue line is the emulator, and the orange line is the shield AMIP case. Again, the dashed line is the reference, and the solid line is our emulator. Basic point here is for these zonal averages of precipitation, air temperature, and winds, the emulator is almost completely overlapped with their target data. So the biases of the emulator against the reference data are much smaller than the difference between the observational data and the model itself, which is good to see. And then, since we do have historical forcing, there's also much more interesting natural variability over time. So we can investigate, say, the response of the precipitation fields to the Niño 3.4 index, create a regression of the emulated precipitation in those cases and compare it to the reference. And in all cases trained on historical data, the emulator almost exactly reproduces the regressed precipitation maps. So, the response to forcing here is very accurate. And you can even see in the climatological case, which doesn't have any, and so in it, you still get some response when running the climatological SSTs through running the climatological SST emulator with historical SSTs. You still see some of that response, but it's a little more muted in value. And then we weren't necessarily expecting this, but because the model does have something that resembles hurricanes, it's not quite the resolution you would need to actually resolve hurricanes, but you can look for warm core structures in low pressure areas over time and compare them between the Era 5 and the emulator. The emulator does a pretty good job of getting the basins correct. So each of these blue lines is a detected tropical cyclone track. So the main point is that the Era 5 and the ACE Era 5 are very similar, and it looks a bit different than the reference shield data, which maybe overproduces or has some different basins that it likes to create tropical cyclones in. So overall, it seems like the emulators can capture this, which is, makes for some interesting ability to look at, how hurricanes evolve in different climates, but still a lot more work to be done there to verify how right or wrong this is. And then also, despite the long-term drifts in the stratosphere, we can look at the sort of the overwinter skill of the zonal mean winds in the polar stratospheres. So in the northern hemisphere in particular, which is more susceptible to polar vortex breakdowns, you tend to see a lot more variability in the winds. And you see that in the ERA 5 data, so that's on the top left. And then the emulator also captures this behavior in the top right. So you see over the course of the winter, you do have some breakdowns where the mean winds sort of reverse directions or get quite weak in that. While in the the southern polar stratosphere where the vortex is much more stable, you see that as well. So you're getting some interesting dynamics that are embedded in the emulator itself that are reproduced that we're not specifically training or doing anything for this, but the model does represent the system accurately enough to contain those, which is pretty cool. So we're kind of just kind of looking around to see what works and what doesn't, and we're seeing some interesting things. Okay, but even more so, climate models generally have multiple components, and not just an atmosphere only that is run forcing, because the more interesting long-term dynamics often involve some coupling between the atmosphere and the ocean. So as the very first move towards this, one person on our team who works at GFDL, Spencer Clark, has been working on ACE2 coupled to a slab ocean model. So in this case, we are no longer forcing from the bottom boundary condition, but we are including CO2. So just a bit about the training data. So we have 3 different CO2 regimes that we train on. One present day CO2, 2 times CO2, and 4 times present day CO2 concentrations. We do include CO2 as an input variable. And then the slab ocean model itself is just a traditional slab ocean model. So some measure of heat convergence in the mixed layer where it's forced by inputs from the atmosphere, which is either the absorbed radiation and turbulent heat loss and emitted radiation from the ocean surface. So we implemented, Spencer implemented that in PyTorch, so it's a fully differentiable model that we can run with this and train ACE alongside it. So our first steps towards actual coupled atmosphere ocean modeling. The first results from that show that the ACE SOM framework is stable both in sample and out of sample for the equilibrium climate. So this is just showing the global surface temperature in the 1, 2, and 4 times cases. And then we test one out of sample case where the equilibrium climate is 3 times present CO2 value. And it gets the equilibrium climate cycle almost exactly on in that case. So generalizes in between at least, which was good to see. And then also it generally gets the pattern of warming correct for that. So on the left is the 100-kilometer shield or FE3GFS run at 3 times CO2 and the response pattern to that forcing on the land. You can see the land surface, the amplified land surface warming. And then the emulator at the 3 times CO2 again shows a very similar response pattern, a little bit closer than the coarse grid climate model run at 3 times CO2. So seems to be doing the right thing here. And then also you can run interesting, out of sample test cases. In this case, if we just do a 2% CO2 increase per year, so at every step, it's sort of seeing a not equilibrium climate anymore, different CO2 values. And so this is again, global surface temperature on the left. The orange is the reference here, and the blue line is the emulator. The orange is a coarse grid climate model reference. The black line is the 100-kilometer reference, which it was trained on. And so you can see it gets the surface temperature gradual increase over time with sort of realistic interannual variability. Same thing for precipitation. But one interesting feature, again, in the stratosphere, looking how that responds obviously to CO2 and changes in radiative cooling with CO2 over time. You see some not realistic behavior here where maybe a slight downtick followed by a full regime shift, and then it resumes the downtrend there. So some interesting things happening that aren't quite right, that are peculiarities of the neural network process. But overall, some of the behavior looks good. So yeah, a lot of interesting things here to study. And then, of course, our next focus areas for this project are moving forward towards actual coupled dynamic emulation models. So this is our collaboration with M2 Lines, maybe some people in the room or online, but they our collaborators there have been working on an ocean model emulator that they can run for similarly long periods of time and maintain realism. So we're working with them to build our ACE atmosphere model and then couple that to this dynamic emulation of the oceans and to see what we can do. Because again, this opens up a lot of pathways that are possible for research and running these models very quickly and doing a lot of cool things. So we're at the very beginning of that collaboration. And then and what I'm particularly involved with is, so we have these climate model emulators maybe run at a coarser resolution than people are interested in for applications. Can we take this output and downscale it to something useful? So we've been using the generative diffusion models that NVIDIA put out a preprint about, notably the core diff process to downscale outputs. And we just have a toy example so far where we're just downscaling precipitation from FV3 GFS from 25 kilometers to 3 kilometers. So here's an example of where that's at right now with respect to a hurricane event off the coast of Florida. So the left is the target image from the 3 kilometer FV3 model. Here's what we generate based on 25 kilometer input, which is shown on the right. So sort of interesting things happening about how we could potentially build an emulator that is also useful for applications. So in summary, we have developed a strategy to create long-term stable, purely ML-based atmospheric models that are suitable for climate prediction. And we're on the pathway, towards creating something that is interpretable, investigatable, and so using some of the traditional strategies that climate modelers have been using. So far, and a lot of the checks we've done, it faithfully reproduces aspects of the reference model's climate. So we've tested in climatological SSTs, AMIP, and slab ocean configurations so far, moving towards emulated oceans, emulated sea ice and land models as well. But also the models themselves seem to capture useful aspects of the forced response to greenhouse gases and atmosphere ocean variability. And again, these models are much cheaper and easier to run than the reference model itself. So really opening up the pathways for people to do interesting projects, science, and checks with this. All of our code is open source. We will have a new release coming soon with some of the latest AMIP model information in it. So be on the lookout for that. And then just in the few minutes before I finish, I do want to talk about sort of the benefits and risks here, because as with all AI-based technologies, there is some amount of risk, even if it is, just for atmospheric prediction here. But the benefits, of course, these climate model emulators represent a significant reduction in the barrier to entry for who can run these and who can use these. And we're already seeing a lot of potential new applications in science, business, and the public where you can fine tune or build these really problem-specific models to do the work for you. But it also offers us a pathway to incorporate the latest really high-quality models that our scientific institutions are putting out, which previously could not be used for climate or other processes, just due to the fact that you're not attached to a large supercomputing center. So it's a sort of a democratization of who has access to these models and who can run them. And of course, the open development of these types of models can really enhance the critical knowledge and information that we have about the growing climate risk market. So about what kinds of outputs are these models giving, and how does that translate to to some risk about the future. But of course, this is a double-edged sword. So because anybody can now make forecasts and project projections and estimate downstream impacts, whether or not the models we create are actually fit for a purpose, people might use it for that purpose. And right now, there's few, if any, standards or regulations about providing risk information to people. So a lot of the climate risk information is being provided right now by companies or insurance providers. Some have skin in the game, some don't. So whether or not the information they're providing is up to a standard may be still an open question. And it's still really early in the research of the limitations of these types of models. So, for example, one particularly dangerous situation in the space of information is that, we put out a climate model. Someone used that to make a decision on a very long time horizon, e.g., like building infrastructure, seawalls, storm drain management. But it really isn't useful for that. And they make this decision. They wasted, a ton of money or put people's lives at risk. So there's clear dangers to, just releasing this and just expecting it to be okay. But it's a little weird because we're already in the space of these black box models from private entities sort of providing these information. But the hope is here that we won't make it worse. So we're thinking about these things, but we're obviously not experts in this. So, we're always looking for people who know more or collaborators who can help us sort of navigate this space because we're obviously not experts and there are risks there. So I just wanted to, thanks for allowing a few extra minutes. I just wanted to add that in. Yeah, that's all I have for you today. A lot of this you can find on our website. Again, we have a lot of open source code for what we've been doing and what we've been working on. If you're interested in that, you can check there and always feel free to reach out. And again, thank you for allowing me the time to talk with y'all. And yeah, I'll be happy to answer any further questions. I can.
Oh, I was wondering during the training for different variables, like the performance of different variables are similar or like some variables are very difficult to predict.
Yeah, it's definitely some variables are easier than others. I think in particular the moisture, or I will say in particular the top level moisture and temperature are harder to predict, so stratospheric quantities, but also the energy budgets right now are not necessarily constrained. So we can look at the moist static energy or say how, the slab ocean model responds to abrupt increases in CO2. And it doesn't seem like the model really has a concept of correct energy flow through the system. So there are definitely some, low-hanging fruit that we're looking to try and improve in these. But in general, the atmospheric temperature or lower atmospheric temperature and humidity and things do quite well, maintain realistic quantities, but it's sort of the budget constraints and top of the atmosphere things that are more problematic right now.
Thanks.
Yeah.
I have another question. So at what point do you,
at what point would you say, like, are there any emulators that are being used for like more operational purposes? And if not, like, at what point do you say it can be, like, would you just basically just check that everything lines up from emulator to kind of source model, or
Yeah.
like, yeah, more philosophical, I guess.
Yeah. So I think that is a big question. It's definitely being wrangled with in the weather forecasting space right now. So, for example, ECMWF has put a lot of resources into building up their infrastructure around providing AI weather forecasts alongside their, traditional medium range forecasts with IFS, so that people can start to make, more long-term justifications of the costs or benefits of just using AI forecasts there. So we're already seeing it kind of happening in that space where they're making decisions about, like, what do we need to run at what, how often do we need to run these really expensive weather models when we have AI forecasts that can do just as well? Are there specific events or types of events where we should run the traditional model and not rely on AI forecasts? So they're starting to draw lines there. I will say probably the US forecasting community is much more behind. But we also have to contend with the fact that we have large technology companies like Google and others who are also trying to provide this information and working on this problem. So we're already seeing operational forecasts probably on your phone that uses some amount of AI. How risky that is maybe an open question. If, someone listens to their phone forecasts about when a thunderstorm is going to arrive and it comes 30 minutes earlier than it says, who's liable for that? Or is there any liability for that? In the climate model space, I definitely think we're much further away from that just because it's much harder to do. I think there's a lot more skepticism for good reason, probably, about whether or not this can work well. But it'll probably be in the next couple of years where we'll really start to see that. And I know, folks are working on medium term, like intraseasonal coupled models. So we'll start to see it creep into that space. And, we will have to, as a community, as a scientific community, try and make, some estimation or start to draw some guidelines about when and where these models are useful or where they break down.
Thank you.
Yeah.
Hey, I was just curious about for the coupled models with M2 lines and slab, like
Yeah.
how did adding those elements impact the performance and like the speed improvements that you were talking about with the first version of it?
Yeah. So the slab ocean model itself, I think, is very lightweight. So it doesn't have a large impact on, say, inference costs. Um, uh, Obviously, coupling to an ocean model is a bit different of a problem because, the M2 lines ocean model runs at a specific time step, whereas the atmosphere runs at another time step. So it's like for every ocean step, you need so many atmosphere steps and running those together, but also meshing them together in some way and having information between. I think it will, increase costs to a certain degree. But these models are so much faster than the original model and, so much faster than it would be to run an ocean model that the cost comparison between, other coupled models, I think will be, the same breakdown where it's the emulator blows it out of the water with respect to how fast you can, get to looking at something, just because the costs increase so much by adding components.
Makes sense. And I'm just curious if you could elaborate a little bit more on like you mentioned that the slab model was implemented in PyTorch. And so I guess I'm taking that to mean that like you managed to encode the math into the model. Is that correct?
The model itself doesn't have a slab ocean. We just have a sort of a dynamical or a dynamic slab ocean model written in PyTorch. So we can run both at the same time, but also back propagate through the joint forecast forward. So the
it's
model itself doesn't have embedded, say, weights for an ocean model or anything. It's just the math was written in PyTorch, so we can
move it to the GPU so you don't have to.
Yeah,
Okay.
exactly.
So
Yeah.
between the two time steps, you're just doing the same math, but on the
Yeah.
GPU and you don't have to move back and forth. Okay.
Yeah,
makes sense.
exactly.
Cool. Thank you.
Yep.